Hey geometers, welcome back to another lesson. This time, in lesson 4, we'll be looking at the mid-segment of a triangle. Let's go ahead and get started. If you are coming from Mr. Forster's class, this is something that we didn't spend a lot of time on, and I don't believe we got to it at the end of first semester. So we're going to look at this formal definition of what a mid-segment is, and then we're going to look at some of the interesting properties and why would we want to learn about this thing, or what makes it interesting when we talk about its relevance in the world of geometry. So our formal definition is the segment connecting the midpoints of two sides of a triangle. So really important, it does need to make sure that it's connecting at the midpoint of those two segments or two sides. Here we see an example in triangle ABC. We have the segment MP is a mid-segment because it connects the midpoint of AB, which is M, to the midpoint of segment or side BC, which is point P. And you'll notice that in each case that it is splitting those sides into two equal segments. Here we're going to look at some of the things that are interesting about these mid-segments. I want you to go through and you're going to go each of these steps, A, B, C, D, and E. And it is important to do them in order because they build along the way. The first one here, using ideally the midpoint formula to get the point M here. Same thing for part B, but this time you're going to look at point N. Next, I want you to use the slope relationship, which is rise over run, or the change in y over the change in x, to find the slope of this segment in red MN. And then you're going to find the slope of our base of our triangle, which is JL. And then hopefully you'll notice something somewhat interesting at that point. So we're going to look at that together. I want you to try on your own, so go ahead and pause the video, and then I will show you the things that I found. All right, if you couldn't quite remember the midpoint formula, I believe we talked about it in the previous lesson video, so you can go back and check that out, or Google is a good friend of yours as well. But for point M, we're going to average the x values of the two points that it is the midpoint of, and that is points J and K. So we're going to take -2 from K and -6 from J, add them together and divide by 2 to get the average of the x values. Same thing for the y values. Again, we have 5 for K and 1 for J here, so we're averaging the y values. This gives us a midpoint at M of -4, 3. And then just a heads up, there's a bit of a typo here. Hopefully you'll notice it, but I'll clarify it in a second as well for part B. Here on part B, this should say N. If you notice that right away, this should say N, but I'm going to be lazy and I'm not going to go back and do a bunch of edits to change this. So just know that this should say N here. And N is the midpoint of points K and L. So we're going to do the same thing we did in part A, but using those points. So we're going to average their two x values, which is this first part. Average their two y values, which is the second part. And again, this should say N, but the point N is at 0, 2. And you say, Forster, but I can just look at the graph, and that may be the case here, but that's not always the case. So knowing the midpoint formula, especially if those points fall somewhere not cleanly on those grid lines, it's helpful to solve for those values independently of the graph. Looking on at part C, we're going to use those 2 points that we just found in parts A and B, M and N, and we're going to find their slope. So slope again is rise over run, so I'm going to find the change in y on top and the change in x on the bottom. And then this is going to give me a slope for Mn of 1 over -4, which can be simplified to -1/4. And then if I look at the same situation here, but this time I'm looking at JL, I want to find its slope. This time again, I'm using the points for J and L. M in this case is going to be still change in y over change in x, but using the points from J and L. This time I get 2 over -8, which at first glance you might think, Forster, that seems to be somewhat uninteresting. But if I simplify it, I get -1/4, which you'll notice, which is part E here, that they are the same. And what that means when they have the same slope is that they are parallel. So this segment MN, this mid-segment, is parallel to the third side of our triangle. So M and N connect 2 of the sides, and it's parallel to the third side. Some other things that are interesting that we can look at, we'll use the idea of distance. So this is using the same triangle in the previous slide, but for the sake of space here, you should be able to see it in your notes, but to make it really easy to read, I have it set up here to where you can't see it. We're still going to use those 2 points M and N for part F. I'm going to pause here though. I want you to try this on your own. I've got the distance formula here on the screen, and I want you to try to apply this for finding the length of MN and the length of JL, and then see if you can find something interesting about that for part H. So go ahead and pause here. Hopefully you worked through this and you found something interesting. If not, I'm going to go ahead and share my results with you. In our first case here, again, we're using points M and N. We're going to take the change in the x values, the distance moving from one x to another, and we're going to subtract those, find that difference, and then square it. We're going to do the same thing with the y values. Again, it's kind of like the Pythagorean theorem in this case, and if you use that, you can use that as well whenever we do distance related things. When we take -4 minus 0, it gives me -4, 3 minus 2 is 1, and then keep in mind that when we square these, we have to square everything on the inside, so -4 times -4 gives me positive 16, so be careful on this one here. And I take this, I add the stuff on the inside, I group everything together on the inside first before I apply my square root, because the square root is applying to that entire sum. I can't do them one at a time. And I end up with this square root of 17, which is about 4.12. Next, we're going to do the same thing for that bottom side, JL. So again, our points are -6, 1 and 2, -1. We apply this, substituting our values into the distance formula. We will get that the x values become -8 when I subtract them. The y values become 2 when I subtract them, and I get the squares are 64 and 4. And then I'm going to take the square root of that sum, which is 68, and I get this 8.24. So you might be thinking, Forster, what's so great about that, or what's so interesting here about these two values? Well, MN here is half as long as JL, or another way to read that is the side of my triangle that's parallel to this midsegment is twice as long as the midsegment itself. So again, the midsegment that we find will always be half the length of that third side, the side that's not being connected by the midsegment. And that gets us to our triangle midsegment theorem. So let's summarize some of these ideas here. The two main things here is that the midsegment is half the length and parallel to the third side of the triangle. So again, when we make this midsegment, we're connecting two midpoints of the triangle. So D and E here are two midpoints of this triangle ABC. And the two sides that it connect are being split in half, but then this third side, interestingly enough, is going to be how we kind of look at this as a point of interest. Well, DE is half as long as AB. It's also parallel to AB. So again, AB is parallel to DE, and DE is half the length of AB. Let's look at some practice problems on how do we actually apply these things. So as usual, I want you to pause the video here, try it on your own, and then I will share the solutions. So read through and try on your own. Let's start with part A. It says we want to find the length of HJ. HJ is this midsegment right here. So since HJ and K are all midpoints, that makes HJ, when they are connected, this is a midsegment. And the midsegment, based on our midsegment theorem, is going to be half as long as the third side. Well, the third side that it's not connected to here is EG, which is 100, which means that HJ is going to be a length of 50. We look at J to K. JK is this segment right here, which is connecting FG and EG. So the third side in this case is going to be FE, which has a length of 60, which means that JK should have a length of 30. Finally, part C for this first row, FG is this entire length all the way across here. And so this is the actual side of the triangle. We have that the midsegment HK has a length of 40, and if that is half as much as the third side, then we can say that the third side should be a length of 80. So FG should be 80. Part D, there's a number of ways that we can write these or order our responses here, but I'll share with you the three ways that I represented this. The first one is I said that HJ is parallel to EG. So HJ is parallel to EG. HK, which is this segment here, is parallel to FG, which is this third side over here. And then JK, which is the length of 30 here, is parallel to EF. or FE. Again, there's multiple ways that we can represent these, but these are the 3 ways that I represented them. Number 5 here. This time we're given some information. We're told that AB is 10 and CD is 26. So I'm going to fill that in on my diagram over here. So I have that this segment here, AB is 10, and this segment CD is 26. So if we were to find EB, well, EB is this mid-segment here. And we know that this side CD is 26. This mid-segment should be half that length, which is 13. Next, we have BC that we're trying to find. And if BC is this segment here, which is congruent to AB, well, that might be the easiest one. We don't even need any mid-segment ideas here. We just need to know that this is the midpoint. So that should be 10. So BC is 10. And then finally, if we're finding AC, if AB is 10 and BC is 10, then we're going to add those together and get AC is 20. Here we have kind of a story problem, or more of a potential practical application of this idea. So we have this walking path, which is from B to D here, and it intersects the sides of this particular park at their midpoints. Maybe the designer of the park or the architect of this particular area was a fan of his geometry class in high school, and he's designed it this way, or she has designed it this way. So it says you walk from park corner A, so you're starting here at A, and you walk over to this path BD, so you're going to be walking along here. Well, if that's 90 yards from B to C, and this is the mid-segment, then this should also be 90 as you walk along this path here. And then it says you're going to walk over the path to the other side of the park, which we already know is 68 yards here from B to D. And then it says you're going to go all the way up to corner E. So you're going to go from D all the way up to E here. If this segment from E to C is 216 yards, well, again, D is the midpoint, so this should be half as long. So that should be 108 yards along here. And then it says you're going to walk back down from E to A, back to where you had began. And how I got this 136 is, well, if B to D is 68 yards, again, that's going to be half as many as this third side here. So if I double 68, 60 plus 60 is 120, 8 plus 8 is 16, so I get 136 here. And if I walk all the way along this path, it says, well, how many yards do you walk all together when you get back to this spot where you end where you began? And I can add these values up, and 90 plus 68 plus 108 plus 136 gives me a grand total of 402 yards. So a little bit more than 4 football fields. All right, finally I have a little bit more of a challenge here on this last problem with adding some algebra practice in here as well. So this time we're trying to find the values of x and y. We have this diagram, there's some midpoints, there's a few mid segments in there on our triangle. In your notes, just a heads up, you're missing this point F. So I added that in there. This point right here is point F. So when you see some of the work, when I share it with you, that's what I'm referring to when I say F. So I want you to try this one on your own, give yourself a few minutes, and come back after you've tried on your own. All right, I'm going to walk through my process here. The first thing I'm going to do is I'm going to find x. The reason that I'm going to look for x first, if I look at the different things that I have, I notice that DF, this is a mid-segment that has a value of x plus 5, and that's going to have a relationship with this third side, but this third side has a y in it. And then if I set that relationship up, I'm going to have 2 variables. That might get messy. If I look at this segment, 2x plus 3, which is segment DE, and then I look at AC, which is the third side, not connected to this mid-segment here. Well, these both are represented with the values, or expressions rather, that only have the variable x in them. So that's going to make my life a lot easier because I don't have to worry about that second variable if I look at some way to connect these two. So the way that I'm going to do that is I know that if I take DE, and if I was to multiply it by 2, double it in length, then I would get the length of AC. And then I can substitute in these expressions for what they represent, which 2x plus 3 is DE, and then AC is this 6x plus 4. And so again, I have 2 times that whole segment, so I've got to keep this in parentheses here and distribute. And then when I do that, I'm going to get 4x plus 6 on the left, 6x minus 4 on the right after distributing that 2 across. If I subtract 4x from both sides, I'm going to get 6 left over on the left, 2x minus 4 on the right. Add 4 to both sides, I get 10 on the left, 2x on the right, which leaves me with a value of x that is 5. So I found x. Now when I go back in and I look at that relationship between df, which has x in it, and bc, which has y in it, well, I can now substitute this value in, and I really will only have to worry about the y at that point. So let's do that next. Let's go ahead and find y. And so I know that df here is x plus 5, which we found x down here. So we're going to now take that value and substitute that in, which means that we can say, okay, df is 5 plus 5 now, which gives me a length of 10 here. And then after that, I can say, well, I know that BC must be 20 because BC is going to be twice the length of DF. So I'm just, instead of setting that up as 2 times 10 equals this, I'm just going to say that I know that BC now is 20. And now I can say, okay, well, 20 is going to be equal to this segment length BC, and it's also this expression 3 minus 1. So now I can set up a relationship that allows me to solve for y. Adding 1 to both sides gives me 21 is equal to 3y. And then finally dividing by 3 gives me a value of 7. All right, geometers, that concludes our lesson 4 from Unit 6. If you have any questions, feel free to reach out. Send me an email or Mr. Swatala an email. But I hope you all have a fantastic rest of your day, and I will catch you in the next one.